All right, hey guys, this is Landon Hicks. We're going to go through rolling today. The goal of this lecture is I want to look at practical ways to solve rolling equations, how they relate to aerospace, and how to use it in MATLAB, specifically for either homework test or for practical applications in aerospace jobs using systems equations to solve rolling problems. So let's look at the first slide. So rolling versus slipping. So of course, the big thing with rolling is that the points in contact need to be at the same relative velocity. The relative velocity to each other needs to be zero. Okay, so if I have 2 points and they're touching in this instant in time, right? So I pause time and these 2 points are touching. They can't have a velocity relative to each other. They can have some linear velocity outside of each other, but them themselves need to be at the same velocity of the 2 points, meaning they are touching. Okay, and so slipping would not have this. Of course, slipping, they will have a velocity relative to each other where they slide. And this is only in a given instant of time. This will change based on in like a couple seconds, but you pause time and look at it. Okay, so when rolling kinematics. Okay, so we have sufficient friction. And the biggest thing that we can see here is that our velocity can be seen by V equals theta R. Okay, so in these kind of equations, in this setup, the main 5 equations we're going to use is we're going to use F net equals ma. We're going to do that in the x and y. Now you're going to see, like, the main thing, you see a slope over here to the left, right? We can put down those, we know that our forces are going to be the gravitational force, the friction force, the normal force, and then we'll have some acceleration to the right down, right? Well, that will be our F net, and we can equal to the a, and that's going to be x double dot and y double dot. So, with the moment of inertia, of course, we're going to get that, then we can solve for these variables using MATLAB later, okay? So, without sufficient friction. So the biggest thing here is that if we look at friction, it has a mu value, right? When it is sufficient friction, this mu value could be used to its max capability, meaning that friction's at its max, kinetic, or it could not be, right? All we know is that it's providing enough. It could provide more, it could provide less. All we know is that it's within the range of providing enough. However, when it is slipping, we know that it's at the zenith of its capability, meaning whatever mu we have meaning we can calculate the mu, because whatever friction is putting out is definitely the max coefficient. So we can use that as one of our equations here. That's the biggest thing with rolling without sufficient friction. Okay. So, and then up here, I went from having the F net equals ma xy to actually solving for the forces that are there, which is mg sine phi, and phi is just the angle of whatever slope that you're at, minus friction equals your acceleration times your mass. Okay, let's see. So, how to solve in MATLAB? So, here's the main functions you're going to use. If you haven't been using this on the test, absolute cheat code. You need to start using this. So, set up symbolic systems of equations with format your equation equals whatever variable equals, and then your variables multiplied by each other. So for example, F net equals m times a, right? That'll be your first equation. You're going to set this up as a systems of equations. That way you can solve them with your solve function later. This allows you to not make any algebra mistakes. I remember the first test was really hard for me by hand. I mean, there's so many errors you can make. MATLAB is the future. You know, if I'm in an engineering job, I really want to be using MATLAB so that I don't make these mistakes, especially on tests when I have a very limited amount of time. All right, so second step, I'm going to use the solve function. The solve function, I'm going to put in an array of my equations and then an array of the exact amount of variables as equations I have. If you have less variables than you do equations, it's going to give you an empty matrix. You want to have the exact amount of variables. These are the variables you're solving for. Remember that I can solve for as many variables as I have equations. So don't put more and then less, it will give you an empty matrix for some reason. I just haven't had success with it. Even if you want to put in variables you're not even trying to solve for, it'll give it to you in the least amount of variables needed. Okay? So then when you go into your subs function later, subs basically takes whatever you made. It goes into this mysol. Notice how I put mysol into the solve. It goes into mysol, and it stores it as a list in mysol. Mysol is an object with 5 properties. If I have 5 values, call it n properties, right? And so I'm going to put my saw, whatever list array that I'm putting, and of course that's going to be based on the order of variables I put in the solve equation. And then I'm going to put the variables after my solve that are within that solution, right? So it's going to be giving me an array with what variables are in the solved portion of the variable you're trying to solve for. You're going to input what variables it shows you it needs, and then the values for those variables on the last portion of that input. Okay, so let's look into some example code. So on the left is with sufficient friction, okay? So sufficient friction, you're going to see I used the 5 equations that I had, and so I use my solve. In this portion, I'm trying to solve for time. You're going to see I use double. Subs often likes to put it in a large fraction. Double really just immediately puts it into the number you're looking for. It'll just immediately put it into one singular number. I put the display just to make it easier to look at. And then sometimes, especially if you have squares in there, it'll maybe have for that solved variable two components. You're going to want to pick whatever one makes sense. Time, of course, I needed that to be my positive one. So say if it's a square root plus or minus, I'm going to choose plus. There is no negative time, at least when I'm solving for just time in general. I guess if there was a change in time, maybe it was negative. Probably not, though. On insufficient friction, we got the same thing. I set up my 5 problems. I use my saw, I use solve. And then I double sum. So I'm still looking for time. And as you see, I put in dg mu phi with the numbers I need, and then I get my answer. So that's about it. So let's see. How does this relate to aerospace engineering? Landing gear. These are wheels that are rolling with a certain friction. Are they slipping on the ground? How fast are we going? This is a very direct, a direct way of using this. Of course, this also gets us more familiar with angular velocity, which is very important. While in there, we have our roll, our yaw, our pitch, and while that's not directly tied to friction, angular momentum, it is with the concept of angular momentum in general. So here are my sources. I use a lot of pictures in this. Thank you for watching, and have a good day.